Okay, in this video, we're going to start talking about energy, right? So the way we're going to talk about this initially is to think about types of energy. So we're going to have a few types of energy. We're going to have kinetic energy, potential energy, gravitational potential energy, elastic potential energy, thermal energy, chemical energy. So we have all these types of energy, and then the addition of all these types of energies is what makes up the total energy. So I know that doesn't define much so far, but these things are going to make sense as we go forward. So let's talk about these forms of energy. What is kinetic energy? It's the energy of motion. If something is moving, we said it has energy. What is gravitational potential energy? Well, it's the energy due to gravity. The higher an object is the more potential energy it has. Elastic potential energy is energy in springs and rubber bands, is that type of energy. Thermal energy is the energy of the motion of the molecules, is the heat energy of an object. Chemical energy is the energy stored in bonds. Is nuclear energy is the energy stored in the nucleus of an atom. So one important thing is that all these types of energy can be converted from one type to another. So you can have kinetic energy converted into potential energy, or kinetic energy converted into thermal energy, chemical energy into gravitational potential energy, and so on. So we can change these energies, and that is an important property of energy. So for instance, here, this weightlifter, when she lifts these barbells, then what happens is she's converting the chemical energy in her body into gravitational potential energy. So in here you have a swimmer, right? Or this, yeah. So there is an elastic potential energy stored here, right? And that elastic potential energy is going to be converted into kinetic energy when he's made to go up. So to understand energy a little bit more, we need to look at the concept of work. And work is one way in which we can transfer energy. So we have a system, and if we want to increase or decrease the energy, if we want to put energy or take energy out, the way we do that is either by work or heat. So work or heat are the two ways in which we can increase or decrease the energy of the system, and the energy of the system is going to be changing from one type to another. So let's see how we can write an equation to relate work and energy. So we have a system, and the system goes from an initial state, right? Initial state to a final state, right? So we do something to the system, right? So the system could be the barbells, right? And then the weightlifter is lifting this barbell, so the barbells increase the gravitational potential energy, right? So we have an initial energy and we have a final energy. And then we talk about the change in energy, which is equal to final minus initial. So now, this change in energy, we're going to write it as the change in all the types of energy that the system has. Change in kinetic energy, change in potential energy, gravitational potential energy, change in elastic potential energy, change in thermal energy, and change in chemical energy. Now, if the energy doesn't change, if this is equal to 0, then the energy stays the same. But if this change here is greater than 0 or less than 0, that means energy was transferred into the system or out of the system, and there was work done to do that. So the change in energy, delta E, for now, is going to be equal to the work done or the energy that is transferred to the system. So if there's no work done, then we call this an isolated system, and the energy, the change in energy is equal to zero, or it is conserved. So that's what the law of conservation of energy says. If the work is zero, then the energy doesn't change. So that means the initial energy is equal to the final energy. So whatever we have at the beginning is equal to whatever we have at the end. So let's start by defining some of these things properly. So let's start by defining work. Work, we said, is the way in which we transfer energy to a system. So work is done by external forces, right? So here you have a force acting on this cell, and the boat is moving this distance d. So, and then we're going to say that the work done by this force is equal to the dot product of F times D. So that's the definition of work. So we can look at in more detail in a scalar form, not in vectors. Is force times D. That's the work done by a constant force producing a displacement D. So the force and the displacement are vectors. Work is just a number. It's a scalar. That is because, well, this is the dot product, right? And the dot product produces a scalar. So don't worry too much about this. So if you're interested in this, I can give you some pointers to read. But for now, think of this just as a number. So units of energy and work we're going to just work in joules. A joule is, well, if you have F times T, this is newtons, this is meters, so joules is 1 newton per meter. So if the force is not parallel to the displacement, right? Here it's moving this way, but the force is going this way, so there is an angle here. So to calculate the work, we take the component of the force parallel to this displacement, that's F parallel. We multiply by the distance this thing is moving, and then we multiply and we get the work. And this F parallel, what is that? Well, that is F cosine theta. So the work in general then is force times cosine theta, that is the parallel component of the force along the displacement, times the displacement. So let's see types of work. So then if the force and the displacement are parallel, then the cosine of theta is 1, and the equation just becomes F times T. If there is an angle that is less than 90 degrees, then between the force and the displacement, then the equation becomes Ft cosine theta. If the force and the displacement are perpendicular, this angle here is 90 degrees, then the work is 0. There's no work being done. If this angle is more than 90 degrees, then this cosine theta is negative and this work is negative. And finally, if the angle is 180 degrees, it's minus Ft, and it is the cosine of theta is minus 1. So let's use those ideas to calculate a simple problem here. We have a suitcase that is being pulled by this tension here, right? This tension makes this angle. The angle is 45 degrees and the tension is 20 newtons. And then it goes a distance of 45 meters, right? So that's the distance. Sorry, 120 meters. That's the distance that it goes. And we want to find the work. How do we do that? Well, this angle here, so we need to find the F parallel, and that is equal to F cosine theta. And then the work would be F cosine theta times D. So let's see. So F is the tension, right? Which is 20 newtons. And theta is 45 degrees. And D is 120 meters. So we can put everything together. We have the force cosine theta, so that's F parallel to D, and then we have D, so 20, 120 cosine of 45 degrees, and that gives you 1700 newtons. So that's the energy that is being transferred to the suitcase. That's the work done by that tension. That tension has transferred 1700 joules of energy to the suitcase. There are forces that do not do any work. For instance, if these barbells are not moving, you know there is a force here, but there is no D. So D is equal to 0. There is no displacement. So therefore, there is no force. Here, we have the displacement in this direction, the force going up. The force doesn't have a parallel component, right? There's no parallel component. Therefore, F cosine theta is equal to 0, and there is no force. Normal forces, they don't produce any work because, well, typically there is no motion in this direction. So therefore, normal forces don't produce any work. Another force that doesn't produce work is centripetal force. Centripetal force is